In this video, I'm going to use simulation software to troubleshoot a recurring problem with a moulding press. The press cylinder's rod seal is failing every 2 to 3 weeks, and my job today is to figure out why. The software I'm using for this task is the very same software that comes included with my home study course, Advanced Hydraulic Control. The first thing I need to do is draw the hydraulic circuit. So I'll begin by dragging the necessary components into the simulation window. Starting with the cylinder, after dragging the symbol in, I use these 3 buttons: rotate, mirror horizontally, and mirror vertically to get the orientation I want. A flow control valve, pilot operated check valve, directional control valve, a check valve, unloading valve, relief valve, pump, return filter, and tank. Now I can connect them. Having now drawn the circuit, I can save it. And print it if I wish. The next step before simulating the circuit is to enter all the relevant system variables. Starting with the cylinder, we're told the piston has an area of 50 square inches, which corresponds with an 8-inch tube diameter. And the ring or annulus area is 15 square inches, which corresponds to a rod diameter of 6.9. We'll assume the cylinder stroke is 18 inches. And because cylinder mounting angle is measured in a clockwise direction, starting from the 9 o'clock position, when orientated rod down, cylinder mounting angle is 270 degrees. Note that I can change between US and SI units of measurement at any time using these drop-down menus. We're told the load on the cylinder is 14,000 pounds, and because it's a hanging load, we enter this as a negative number. The pilot-operated check valve has a ratio of 4:1, and I'm going to enter an arbitrary figure for hydraulic resistance. Same again for the flow control valve. The directional control valve. The check valve. The solenoid unloading valve. And the filter. Now the pump. And lastly, the relief valve, which limits system pressure to 1600 psi. Now the hydraulic circuit is ready to simulate. But before I do, and since this circuit is electrohydraulic, there are two options for shifting the solenoid valves during simulation. I can create the necessary electrical control circuit or shift the valves manually. To demonstrate both options, I'll build a simple electrical circuit. There are 3 solenoids, which I'll now label. And these 3 solenoids are replicated in the electrical circuit. Due to their current draw, valve solenoids are switched using relays. Relay K1 will energize solenoids S1 and S3 simultaneously to extend the cylinder, and relay K2 will energize solenoids S2 and S3 simultaneously to retract the cylinder. So when this push button is made, relay K1 is energised, which closes these two contacts, labelled K1, energising solenoids S1 and S3, which loads the pump and extends the cylinder. When this push button is made, relay K2 is energised, which closes these two contacts, labelled K2, energising solenoids S2 and S3, which loads the pump and retracts the cylinder. Before proceeding, I'm going to change the simulation colour for electrical active to distinguish it from high pressure in the hydraulic circuit. Let's now confirm correct operation of the circuit. As mentioned earlier, I also have the option of shifting the solenoid valves manually without the need to create the electrical circuit at all. Now we're ready to analyse the recurring failure of the cylinder's rod seal. To assist in this exercise, I'm going to install pressure gauges on both sides of the cylinder. Take note that at any time I can switch between US, UK and SI units with a couple of mouse clicks. As you can see, the system appears to function okay, but since the rod seal keeps failing, it would be helpful to quantify the pressure on the rod end of the cylinder across its entire stroke. But just like in the real circuit, the simulation is happening too fast to enable this. So there are a couple of things I can do. The first is to slow the simulation down. With the simulation slowed down to 10 to 1, we can see, if we take note, that there is a pressure spike when the cylinder starts to extend. It's still difficult to get an accurate fix on the magnitude of this pressure spike and the state of the other components in the circuit when it's happening. But I can explore this further using another feature of the software. By using this button, Simulate Until State Change, I can advance the simulation in steps. With this push button mode, relay K1 is energized, which then closes these two contacts which simultaneously shifts the unloading valve and directional control valve. Then this check valve opens, then pressure starts to build on the cap end of the cylinder. And now we can see the crux of the problem. Pressure on the cap end of the cylinder has risen to nearly 1400 psi, and yet the pilot operated check valve is still closed, with the result that the pressure on the rod end of the cylinder has risen to 5500 psi. The next state change shows the PA check opens and the cylinder extends. Given that the cylinder is only rated to 2000 psi, this pressure spike certainly explains the recurring failure of the cylinder's rod seal. But why is this happening, and how do we fix it? To analyse these questions further, I'm going to use a spreadsheet I created in Microsoft Excel. For those of you not familiar with Excel, I strongly encourage you to fix that, because it's a very useful tool for hydraulic system analysis, and that's why an entire module on how to use it is included with my home study course, Advanced Hydraulic Control. In the case of the moulding press, there are 5 variables which influence the magnitude of the pilot pressure required to open the check valve, and by extension, the pressure developed on the rod end of the cylinder just prior to the check valve opening. As you can see, I've already keyed the necessary formula into these yellow shaded cells, so that when I enter all the required data in these cells, Excel will solve the equation. Load-induced pressure. We have a load of 14,000 pounds being supported on an area of 15 square inches. So 14,000 divided by 15 equals 933 psi. Check valve ratio, we know that's 4:1. Cylinder area ratio, piston to annulus, 50 divided by 15 equals 3.33 to 1. Check valve spring constant is not applicable in this case. Residual pressure at the A port of the PO check, 8 psi. So according to this calculation, the pilot pressure required to open the check valve is 1,436 psi. Meanwhile though, the pressure in the rod end of the cylinder will rise to a calculated pressure of 5,720 psi before the check valve opens. The benefit of having done this calculation in Excel is we can now change the input parameters and instantly see how they affect the result. That said, I could also change the parameters in the simulation software directly without using Excel. So what if we reduced the cylinder's rod diameter and thereby increased the annulus area to say 20 square inches? Clearly this would work, but without further investigation we don't know if the reduced rod diameter can handle the load, and in any case this would require changing out the cylinder, which is certainly not ideal. It's fairly obvious that the easier variable to change is the ratio of the PO check valve. Ultimately, the ratio chosen would be determined by the actual availability of a suitable valve. But let's use a ratio of 8:1 in our model. This simulation confirms that we have now identified and fixed the cause of the recurring rod seal failure. And it also demonstrates that with the right tools and tuition, you can become a troubleshooting wizard in a very short space of time. So don't envy us, join us. Start today by following the link below.